Dear students, in last class we discussed ionization due to metastable and neutral atoms. In today's class, we shall be discussing Townsend's theory. In that first we will take up Townsend's first ionization coefficient. Townsend's first ionization coefficient. To understand what is Townsend's first ionization coefficient, we shall consider the same arrangement which already we considered in previous explanations. Here again we are having two electrodes, namely cathode and anode, adjustable HV source, ammeter and current limiting resistor. Here is gas medium. The distance between two electrodes is D. Let us say we measure the distance from cathode to anode as x, right? At x equal to 0, we are at cathode, and at x equal to D, we are at anode. Previously we studied that cathode emits electrons due to various reasons, maybe due to excitation voltage or maybe due to photons falling on it, etc. Now let us consider n0 number of electrons are emitted from the cathode. Initially, I will show those n0 electrons from the cathode. That means at x equal to 0 units. So right here now, let us assume that n0 electrons are emitted from the cathode. So next what happens? When one such electron collides with one neutral atom of gas or one molecule of gas, one positive ion and one electron will be liberated. When one electron collides with a neutral particle, particle means atom or molecule of gas, a positive ion and an electron are formed, and we know that this is nothing but an ionizing collision. So this is called what? Ionizing collision. So we are going to get here one ion and one electron. Let alpha be the average number of ionizing collisions made by, let alpha be the average number of ionizing collisions made by an electron per centimeter. Travel in the direction of the field. Here the field is directed from cathode to anode. It is field direction. Now electron formed here and the electron given out here are moving in the direction of field. Now let us say this electron makes alpha number of ionizing collisions per centimeter. This alpha depends on gas pressure P and E by P and is called Townsend's first ionization coefficient, and E here is the electric field magnitude. At any distance x, from the cathode, let the number of electrons be nx. when these NX electrons travel a further distance, say dx, that means a very small distance, they give rise to alpha nx dx electrons, because we know that number of collisions made per centimeter is alpha in the direction of the field, and that is by one electron. If there are nx number of electrons, then alpha into nx into dx number of collisions will be made when dx distance is covered. At x equal to 0, we know that nx equal to n0. Also, dnx by dx is equal to alpha nx, or nx is equal to n0 into e to the power alpha x. This we get by integrating this equation. Then the number of electrons reaching the anode. Anode is at what distance from the cathode? It is at d distance. That means if we put d in place of x, we get the number of electrons reaching the anode. That is at x equal to d will be nd. That is in place of x here I am going to put d. And what will be that? That will be equal to n0 into e to the power alpha d we will put here, because x is equal to d now for us here. The number of new electrons created on the average by each electron is exponent of alpha d minus 1 equal to nd minus N naught divided by N naught. To understand how we got this relationship, you refer to the derivation here. Therefore, the average current in the gap which is equal to the number of electrons traveling per second will be, because current means rate of flow of charges, I equal to I naught into exponent of alpha d, and this current equation we are getting by replacing nd by I and n naught by I naught in the equation for nd. And now this I naught represents initial current at the cathode, where I naught is the initial current at cathode. Since current at a distance of d from cathode, that is at anode, is exponent of alpha d times the current at cathode, exponent of alpha d is called current amplification factor. I will just brief what we learnt in the Townsend's first ionization coefficient. At cathode, n naught number of free electrons were emitted, and those n naught number of electrons collided with n naught number of atoms at the cathode and released n naught number of ions, that is positive ions, and n naught number of electrons. Please remember, this is at cathode, that is at x equal to 0. And as they started moving towards the anode, the n naught number of electrons collided with more and more number of gas atoms or molecules and released more and more number of ions that is positive ions and electrons, according to Townsend's theory. And finally, Nd number of electrons reached the anode, that is here. And this Nd is very large because when N0 number of electrons move from cathode to anode, there will be large number of collisions and hence large number of electrons will be produced, and those all electrons will reach the anode. See, N0 number of electrons becoming large number of electrons Nd is called as Avalanche breakdown. What it is called as? It is called as Avalanche breakdown. And since here we are considering only N0 number of electrons making collisions with the gas atoms and producing electrons, and because of that large number of electrons, that is Nd number of electrons reaching the anode, is called as single avalanche process. Is called as what? Single avalanche process. Now we will take up current growth in the presence of secondary processes. The single avalanche process discussed previously becomes complete when initial set of electrons reach the anode. However, since the amplification of electrons by what factor? By a factor of exponent of alpha d, is occurring in the field. Where is the field? Field is between anode and cathode. The probability of addition of new electrons in the gap that is between the electrodes by other processes increases. And these new electrons create further avalanches. The other processes are first one, the positive ions liberated may have sufficient energy to cause liberation of electrons from the cathode when they impinge on it. Referring to the figure here, these positive ions being attracted by the cathode, when they impinge on the cathode, they will also liberate some electrons because they have got sufficient energy in them, right? And the electrons so liberated will be creating further avalanches. They will be creating further avalanches of electrons in the gap. Second process, photoionization. The excited atoms or molecules in avalanche may emit photons. And this will lead to the emission of electrons due to photoemission, which we have discussed already. The metastable particles means atoms or molecules, may lead to emission of electrons. And we know that the electrons emitted by all these processes are called the secondary electrons. The electrons emitted by these processes are called secondary electrons. As we defined primary ionization coefficient alpha, on the same lines we can define secondary ionization coefficient gamma. The secondary ionization coefficient gamma is defined in the same way as primary ionization coefficient alpha. As the net number of secondary electrons produced per incident positive ion, photon and metastable particle and the total value of gamma is the sum of the individual coefficients due to the three different processes explained above, right? That is gamma equal to gamma 1 plus gamma 2 plus gamma 3. Gamma is called the Townsend's secondary ionization coefficient. And is also a function of the gas pressure P and E by P, as alpha was the function of these two quantities. Following Townsend's procedure for current growth, let us assume N0 is number of secondary electrons produced due to secondary processes, and let N0 double dash is equal to total number of electrons leaving the cathode. Then N0 double dash is equal to N0 plus N0 dash, where N0 is the number of free electrons emitted by the cathode and N0 dash is number of secondary electrons produced due to secondary processes. The total number of electrons reaching the anode becomes N equal to N0 double dash exponent of alpha d, that is N0 plus N0 dash into exponent of alpha d, and N0 dash is equal to gamma into N minus N0 plus N0 dash. Eliminating N0 dash in the expression for N that we have written above, n may be written as n naught into exponent of alpha d divided by 1 minus gamma into exponent of alpha d minus 1, or I is equal to, simply I am going to replace here n by I, n naught by I naught. I equal to I naught into exponent of alpha d divided by 1 minus gamma into exponent of alpha d minus 1. Now we will study Townsend breakdown mechanism. We have expression for current I when gas medium between the electrode breaks down as I equal to I naught into exponent of alpha d divided by 1 minus gamma into exponent of alpha d minus 1. This current will become infinite if the denominator becomes equal to 0. I tends to infinity as 1 minus gamma into exponent of alpha d minus 1 becomes equal to 0. But alpha d is very large, therefore exponent of alpha d is much greater than 1. Hence we can write one minus gamma into exponent of alpha d equal to 0, or gamma into exponent of alpha d is equal to 1. The condition gamma into exponent of alpha d equal to 1 defines the condition for beginning of spark and is known as the Townsend criterion. for spark formation. Or Townsend breakdown criterion. Using the above criterion, the following three conditions are possible. First one, gamma into exponent of alpha d equal to 1. So if I put gamma into exponent of alpha d equal to 1 in the expression for current I, then current I becomes equal to infinity with the assumption that exponent of alpha d much greater than 1. It means that the number of ion pair produced in the gap by the passage of electron avalanche is sufficiently large, and the resulting positive ions on bombarding with the cathode are able to release one secondary electron and so cause repetition of the avalanche process. The discharge is then said to be self-sustained, as the discharge will sustain itself even if the source producing I naught is removed. Therefore, the condition gamma into exponent of alpha d equal to 1 defines the threshold sparking condition. So I'll just have a note of it. The number of ion pairs produced in the gap by the passage of electron avalanche is sufficiently large and the resulting positive ions on bombarding with The cathode are able to release one secondary electron. And so cause a repetition of the avalanche process. The discharge is then said to be self-sustained. As discharge will sustain itself even if the source producing I naught is remote. Therefore, the condition gamma into exponent of alpha d equal to 1 defines the threshold sparking condition. Second condition may be taken as gamma into exponent of alpha d greater than 1. Here, ionization produced by successive avalanche is cumulative, which means the positive effects will go on adding. The spark discharge grows more rapidly as gamma into exponent of alpha d becomes more and more than unity. Third condition, if gamma into exponent of alpha d becomes less than 1, then current I will not be self-sustained. That is, after removal of the source of current I naught, it will cease to flow. Dear students, I will stop the class here and continue in next class with streamers theory. Thank you.